So it is titled Graphing Inverse Trig Functions, but really we're just exploring inverse trig functions in general. So just like an inverse function, like an opposite operation, add, the opposite of adding is subtracting, opposite of multiplying and dividing, opposite of squaring is square rooting. The opposite of sine is an inverse sine. They have functions that undo them. So if you think about it, trig functions themselves, that's sine, cosine, tangent, they take an angle as an input, so you plug in an angle, and they give you out a value like 1/2 or square root 3/2, all of those things. So we get out a trig ratio. An inverse trig function is going to work the opposite way. You will input a value, and you will get an output of an angle. So this time we're essentially working backwards. Inverse trig functions, you don't plug in angles, you plug in like 1/2 or square root 3/2. You get out an angle. They're just opposites of each other. The inverse of sine is written two ways. It is written as sine, wrong color, sorry. Sine inverse of x, or sine to the -1 of x. Notice that the -1 is next to sine, not next to the x. Or arc sine of x. Was this on your UIL stuff? Yeah. Arc sine or inverse sine. Cosine's inverse is cosine -1 of x. It's called inverse cosine. Or you can write it as arc cosine. Those are interchangeably the same thing. They have two different names. And last but not least, your tangent, pretty obviously, is tangent inverse or arctangent. We don't do inverses of secant, cosecant, or cotangent, so the reciprocals we don't have to really worry about. Technically, they're just the reciprocal of this, but not needed to do the inverse of that. But just a quick reminder about inverses in general. When we studied inverses in like September, we said that inverses must be what's called 1-to-1, which means it passes both the vertical line test and the horizontal line test. So let's perform those tests for these. Actually, we'll do that after lunch. And how things that are 1-to-1 need to pass the vertical line test and a horizontal line test. So let's look at sine first. Does sine pass the vertical line test? Yes, it is a function, so it passes the vertical line test. So we're going to write pass. Yay. Does it pass the horizontal line test? Oh, no, it doesn't. So that is a problem. Okay. Put a little frowny face there. Fail. Okay. What about cosine?
Yes.
Yes for the vertical line test. What about the horizontal? No. Again, it fails. So that's another problem. What about tangent?
Yeah.
It passes the vertical line test. It is a function. But does it pass the horizontal? No. Okay, so we have a bunch of problems here. We know that there are inverse functions, because I've already told you that. But there's not, because it doesn't pass the horizontal line test. So this is a problem unless we figure out how to restrict the domain of these functions so that they do pass. When we're talking about restricting the domain, we're talking about looking at only a very specific part of the graph so that the vertical line test and the horizontal line test is a pass. So if we look at sine, and if I were to take sine and I were to chop it off here to here, meaning we're only really looking at this section here in the middle. Ignore everything else. Does it pass the vertical line test?
Yes.
Does it pass the horizontal line test?
Yes.
That means that we can restrict this domain between those 2 points. Now, if you look at the pattern, you think back to the x increment, that is at a maximum and a minimum, which is 1 step away. That means this is at positive pi over 2 and at negative pi over 2. So if we restrict its domain between those two x values, we have the part of the function where it is defined, where we would have a pass for HLT and VLT. It's going to be a different set of numbers for cosine. How can I restrict cosine to make it pass the horizontal line test?
On the left side of the minimum to the max.
So from here to here, right?
Maybe almost the same.
Essentially, yeah. So you said it backwards, but yeah, essentially this little section right here, if you perform the vertical line test, it passes. If you perform the horizontal line test, it passes. That is from 0 to pi based on the pattern that we know for x increment. Now, what about tangent? Indeed.
Ooh, from that to that.
What?
That.
So we want to restrict the domain. So we're looking at, again, at putting like
You put it on the bottom, not the top.
like this?
Yeah.
No.
You can do that.
Well, you could, but that's restricting the range. We want to restrict the domain.
Oh, then -1.
Are you kind of talking about like here to here? If we look at just this wave for tangent, does it pass the vertical line test?
Yeah.
Does it pass the horizontal line test?
Yeah.
So that little section of tangent will have a defined inverse function. That is from -pi/2 to pi/2. It's at 2 different vertical asymptotes, if that clicks in your mind for the x increment. So this one now passes both the horizontal and the vertical line test. So what that means is that when we are performing inverse functions, we have a very specific window of where that can happen. And that is on the next page. So if you look on this page, sine of x can only appear on the interval between -pi/2 and pi/2, which is what that picture is for you on a calculator screen. It has a minimum, a center, and a maximum in between -2 or -pi/2 and pi/2. So if we were to look at the domain of this function is from -pi/2 to pi/2. What is the range of just this little section? What's the range?
-1 to 1.
-1 to 1. So we're choosing to restrict the domain and pretend like sine only exists in this interval, which means that the inverse, which remember, inverse is switching x's and y's, is literally just going to do this. The domain of the inverse function is between -1 and 1, and the range of the inverse function is going to be between -pi/2 and pi/2. Now, why that's important is because when we are doing arc sine or inverse sine, this number right here, anything between -1 and 1 are numbers you can plug in. That's what a domain is, numbers you can plug in. Meaning that our output or our range are going to be angle measurements we can get out. So if you get an angle measurement out of an inverse sine that's somehow bigger than pi/2 or smaller than -pi/2, something wrong. And what that means graphically in the unit circle is that sine is going to appear, inverse sine is going to appear in these two quadrants. That's -pi/2, and this is pi/2. When we have values that we're taking that are positive, we'd be in quadrant 1. When we have values that we are taking that are negative, you'd be in quadrant 4. So you should have some sort of negative output value. So it changes our domain and range. Because normally sine, if you think about it, was quadrants 1 and 2. But for inverse sine, it's quadrants 1 and 4, which is interesting. Let's do the same idea for cosine. Based on how we had to restrict cosine, the domain for cosine is going to be from 0 to pi, but the range is still from -1 to 1. Inverse cosine is going to be the inverse of that, switching the x's and the y's. Meaning the domain of arc cosine is from -1 to 1, and the range is from 0 to pi. You are allowed to plug in numbers from -1 to 1 into arc cosine. You should get out angles between 0 and pi for arc cosine. If you get something out that's bigger than pi or smaller than 0, you did something wrong. But what that means here, we are no longer working in quadrants 1 and 4 like we were for sine. These are going to be in these two quadrants because this is 0 and this is pi. Positive cosine values will come from quadrant 1, and negative inverse cosine values will come from quadrant 2. Inverse tangent, same thing that we've been doing. Regular tangent that we restricted has a domain of negative pi over 2 to pi over 2. But what's its range? All real numbers, so from negative infinity to infinity, because these arrows are going to go off screen all the way up and all the way down. So when we do inverse cosine, inverse tangent, I can talk, right? The domain is going to be all real numbers, and the range is going to be from negative pi over 2 to pi over 2. So you can plug in any number into arctangent, and you should be able to get an angle out of it. The angle should be between negative pi over 2 and pi over 2. So since this range is the exact same as sine, tangent will also happen in these two quadrants. So it's exactly like sine, where the positive are in quadrant 1 and the negative are in quadrant 2. 4. Oh my gosh, 4. So you plug in any value, you get out an angle between negative pi over 2 and pi over 2. So what's the point of all this? Well, the reason we had to wait to do inverse tangent, inverse sine, and inverse cosine, it's more of like goes in our trig angles unit, is because it relied on our ability to graph the functions to know about the restrictions. So yes, we have the graphs of them. They're very small because that's literally it. Can't really change it much. But what it's going to do is it's going to help me be able to actually find inverse cosine, inverse sine, and inverse tangent angles. Essentially, help me work backwards in the trig that I've been doing. So obviously, I've got your table here again. This is why I needed you to remember it, because we're actually going to use it today. We're going to combine the sine, cosine, and tangent circular graphs onto one here so that we have a good reference. But before we do that, it will be very helpful if you have the coordinate points labeled around this unit circle. What's the coordinate points for this first one right here? The first dot at 0. For a unit circle? Something, comma, something? We're overthinking it.
Yeah.
1, comma, 0. What's the coordinate at the top? 0, comma, 1. What's the coordinate at 180 degrees? Okay, and then the coordinate at 270. Cool. It's helpful to remember that. It is also helpful to remember as we are working around this unit circle that the x values are cosine and that the y values are sine. Not inverse, just regular sine and cosine like we've been having. Okay. Might be helpful to have 3 different colors at this point to show 3 different things. If we were doing sine, we said that sine can appear in the first quadrant, inverse sine, and in the fourth quadrant. So that means sine can take these 2 quadrants, inverse sine. Which 2 quadrants was inverse cosine allowed to be? 1 and 2. So inverse cosine is in 1, inverse cosine is in 2. So that means that this color would be these 2 quadrants. And lastly, we have tangent. Which 2 quadrants is inverse tangent defined? 1 and 4. So same thing as sine. So that means inverse tangent can be here. So all 3 are in quadrant 1. They're all going to be positive in that quadrant. Sine and tangent are in 1 and 4, defined in 1 and 4, and inverse cosine is defined in 1 and 2. Between the table, which I've put here as a quick reference, even though we should have it memorized, and this new unit circle situation, we're going to be able to perform inverse cosine functions from just the table and just the unit circle. So what that means is, if I ask you to find the exact value, first of all, we're going to work in radians, so no more degrees. If I ask you for inverse cosine of 0, 0 would be the number we got out if I asked you to take cosine. So what I want you to do is I want you to look around. I'm not going to zoom to show you, but you can look at yours. Look around that unit circle for places where cosine is 0. Okay, cosine is the x value in those coordinates. So what places is cosine equal to 0? So it should be 2 specific places. If I'm looking at this, I'm looking for where the first coordinate point is 0. Nope. Yep. Nope. Yep. So I have 2 places on this unit circle where cosine of is 0. Which one of those 2 places is in the section that is defined for cosine? The top one, because cosine is only defined here. So what's the angle measurement there at the top of the circle? Ooh, in radians. That's it. So cosine inverse of 0 is pi over 2 because regular cosine of pi over 2 is 0. These are inverses of each other. Regular cosine, you put in an angle, you get out of value. Inverse cosine, you put in a value, you get out of angle. Okay, similar question, but we're going to do it with sine. Inverse sine of 0. So look through the table, look through the unit circle. Where do you see sine being equal to 0? Should be 2 places. So like on the x-axis. So this one and this one. Okay, great. Cool. So we have 2 places where sine is equal to 0, but inverse sine is only defined on one of those 2 places. Which one? Because sine is only defined from negative pi over 2 to pi over 2. There's only one option. So inverse sine of 0 is equal to 0. That is the angle measurement 0. Okay, some of them are a little bit easier, like this next one. The next one we're asking for arc sine or inverse sine, those are interchangeable, of 1 over square root 2. Well, first of all, I hate that they wrote it as 1 over square root 2, so we're going to go ahead and rationalize that denominator. Cool. Do you see anywhere on your table or on your circle where sine is equal to square root 2 over 2? Do you see anywhere on your table where sine is equal to square root 2 over 2? Yeah, what's that angle measurement? 45 degrees, but in radians. We're working only in radians. Pi over 4. That's it. So when you have, this is an important note for yourself. When you have positive values as inputs, they are in quadrant 1, which means they are in your table. They're going to be easy. Yes? Okay, prove it to yourself. In question D, I want the arc tangent of 1. Does 1 appear anywhere in the table or on the circle for tangent? Yeah, where? Ooh, in radians though. Pi over 4. That's it. I'm done.
I only know the difference.
I gotta learn the radians. Now again, we know this is true because the tangent of 45 degrees, or pi over 4, is 1. That's a fact we know. So arc tangent is just literally the inverse of that. Switch the x and the y. Switch the input and the output. Okay, you've got this one. Cosine, or inverse cosine of 1/2 in radians, though. Do you see 1/2 anywhere for cosine?
Oh, yeah.
Yeah, what's that angle measurement? That's it, pi over 3, 60 degrees. Okay. Now, some of them are not going to be positive, so they're not necessarily going to be as easy-ish. Notice here I'm asking you for the inverse tangent of negative pi over 3. Imagine for a second it didn't say negative. I think I said pi over 3. Do you see square root of 3 anywhere in the table for tangent? Yeah. Okay. What is that tangent? Wait, so what'd you say? Thank you. So we know that tangent of pi over 3 is equal to square root of 3. We know that. That's going to be a huge hint for us. But we want negative square root of 3. So we have to think for a second. For it to be negative, it needs to be in quadrant 2. Okay, well, how do I go from here to here? Yeah, what is the reference angle? Well, let's not think of it as reference angles because reference angles is neither positive or negative. This one is going to have positive or negative. I think we're thinking too hard. This distance is also pi over 3. But since now I'm working in a negative direction, it's just going to be negative pi over 3. Because remember, we've defined this as negative pi over 2 and pi over 2. So we're allowing ourselves to have negative angles because that's how this function is defined. One note for you, because I asked this question a lot when I was learning this. I was like, okay, well, yeah, we can go this way. That's fine. But can we go this way? It gets you to the same terminal side. Why is that going to not be allowed?
Because it's a negative way. Because if it were positive, then you would go counterclockwise.
Uh-huh. But we only have the value. We don't necessarily have the angle. Why would I not be allowed to, like, come here on the circle? It's not tangent on that side. Inverse tangent is only defined in these two quadrants. So can I at all follow that blue arrow? No, I'm not allowed to go in quadrants 2 and 3 for tangent. So I know I can't go all the way around and make the angle really big. I have to use the short angle, which is going in negative or clockwise direction. So don't get tempted to do what we did before, because inverse tangent can't do that. You're going to have negative values here. Here, make that annotation. No, just in case you forget later. Okay. Tangent and sine, really simple when they're negative, because we know we're just going the negative direction for what is represented in the table. So think for a second, if it was just arc sine of positive square root 3 over 2, how would you answer that? Where on your table does sine have square root 3 over 2? For sine? Pi over 3. Okay, well that would be if it was positive version, but if we're going negative version, for sine, we just need to go negatively.
So you would just put a negative where there's a negative?
Yep. For tangent and for sine. But cosine is not so simple. For arc cosine, I honestly, if you are using a highlighter, this is probably one of the most important examples on our notes today. I would emphasize this one. Because arc tangent and arc sine, very simple. You just slap a negative on the value from the table because you're just going clockwise, which is a negative direction. However, cosine cannot go negative because cosine is only defined in quadrants 1 and 2, inverse cosine. So your note for yourself is going to be that cosine inverse of negative number requires work. That's all we're going to say. I know, it's not as simple. It is still simple, but it's not as simple. It is going to require work. Okay, here's the work we would show. Arc cosine of negative root 3 over 2. Where do you see root 3 over 2 for cosine? So pi over 6. So if I knew that the reference angle I created to make this happen would be pi over 6, because in quadrant 2, you wouldn't use the exact angle, you would use the reference angle. That's what we did before. But that is not the angle that we're taking the arc cosine of. The angle that we're taking the arc cosine of is actually this guy. It's all in quadrant 1 and quadrant 2, so it's allowed to be that direction instead of going negatively like the others. We just need to figure out what that value is. But if this is pi, which is 6 pi over 6, and you're taking 1 less than that, what is the value of arc cosine? 5 pi over 6. So you had 6 pi over 6, you take 1 away, it's 5. Yeah, don't ever think that part.
Wait, how did you get 6 pi over pi?
Because normally the 90 degrees is pi, so if I needed to have matching denominators, it'd be 6 pi over 6. I wanted to match with this, and you got this out of your
It's
table.
because you put 6 pi over pi.
Oh, oops.
Yeah.
6 pi over 6. My bad. Thank you.
So 150 degrees.
Yes, but we're working in radians.
Dude.
So when you have negative with cosine, that's the one that I highly suggest drawing a reference angle for and then doing what we did previously. Arc tangent and arc sine, easy, make it negative. Arc cosine requires work. Okay, well, let's go back. Now we have arc sine, but it's of a negative number, no panicking. What is the arc sine of positive 1/2? Pi over 6, so the arc sine of negative 1 over 2? Negative pi over 6, very good.
I like these questions. Can we keep having them?
Yeah, we can keep doing them.
Wait, go back.
Going back, I'm going back. That's it, that was it.
Hello, do you understand?
Okay,
How many degrees is that? How many degrees is that? 30.
negative 30.
Negative
30.
What would it be?
Degrees, I can't be negative, can they?
They can. It just goes clockwise instead of counterclockwise. Okay, arc sine of square root 3 over 2. Again, it's all positive, so it's very simple. Where does square root 3 over 2 appear for sine? Pi over 3.
Wait,
Okay. Arc sine of 2. So first issue, does this appear in my table anywhere? No. Here's the problem. Think back to the page before this when we said that there was a set of numbers we could plug in. So flip back to sine for a second, to arc sine when we talked about it. What was the range of arc sine? Sorry, the domain of arc sine.
it's still 45, because 45 has a 1. You double it.
Hold on. Look at that page right before it. What was the domain of arc sine? Negative 1 to 1, which means, and we've been doing this the whole time, you just didn't notice, all of the numbers we've been plugging in have been less than 1 or greater than negative 1. So they've been in this range. Is 2 in this range? No. If it is not in the range, that means I can't actually plug in the number 2. It's out of bounds. This is too big. Yeah, we're writing this down so you remember what's happening in your notes. You don't have to ever write something like this. Here's what you write. What do you think that stands for?
Does not exist.
Does not exist. You cannot take the arc sine of 2. It does not exist. It is outside of the boundaries of the graph that we had to use because it's the inverse of sine and cosine, which is negative 1 to 1.
Sorry.
No, yeah, go ahead.
So if you were to put that in the calculator, it would pull up D and E?
It would specifically tell you error domain, which is cool because the error is in your domain. Yeah, it says error domain. Okay, last one. Easy peasy. What is the arc cosine of square root 2 over 2? Pi over 4. But we're going to make a little extra bonus question here. What if I asked you for the arc cosine of negative square root 2 over 2? That is the funniest looking square root 2 over 2. Okay. Here's what we do. You draw yourself a picture. We know in quadrant 1, square root 2 over 2 for cosine refers to a pi over 4 angle, 45 degrees. I need that in the negative one. This reference angle is pi over 4 because the cosine of pi over 4 is square root 2 over 2. But I don't want to answer with that angle. To answer the inverse, I want to answer with this angle. What is that angle? In radians.
Oh, because that's pi over 1/2. No, it's 4 pi over. No, it's 4 over pi. 3 pi over 4.
It is 3 pi over 4. How'd we figure that out is a great question. Remember, this right here is pi, and if I want it to be the same denominator, it would be 4 pi over 4. So we take 1 away. We're at 3 pi over 4. So really, this is very, very simple unless it's a negative input value for cosine only. The rest of them are very, very simple. But we know how to draw pictures, and we can subtract 1 or 2 from pi. This is definitely the most important part for you to be able to complete your homework. So keep this available for you so you can look at the table and reference it until we have it all memorized. And all of the answers are in radians. Okay. Last thing here, I just thought it would be nice to have pictures of all of the different functions that we've been using. This is just a reference page for you. So you have nice pretty graphs for sine, cosine, tangent, cosecant, secant, and cotangent, and then our inverse functions. So that's just a reference sheet for you to get used to what the shapes look like for all of them.